eigenvalues. Okay, this is the sections I will discuss. First is section general stuff on resonances. Then resonances is in the sense of almost exponential decay. Then a chapter on Raglan perturbations. Then an application to finite multiplicity operators, and a concrete example on a Sturm-Liouville model. If I have time, I will tell you about this boundary limit of Borel transforms, which is some technical stuff that has some interest on itself that we needed in the proofs. The subject of resonances in quantum mechanics is very long. It's a long one, and there are many approaches. And here we will discuss essentially two. Well, actually only one, but it has some closely connection with a second one, which is probably the most popular, and which characterizes resonances as poles of a suitable meromorphic continuation of the Hamiltonian from the upper half plane to the lower half plane, complex plane. In this continuation, resonances appear as poles of the continued resolvent, and they are eigenvalues with the negative imaginary part that correspond to generalized eigenfunctions that are not in the Hilbert space. But there is another characterization in which you have some sort of exponential decay of the time on the time, in the sense that I will describe immediately. This has to do with this so-called survival probability, P sub phi of t, given there, the inner product of phi with the evolved state, e to the minus h t phi squared, and which is the probability of finding the system at time t in its initial state phi. This is the quantity, actually what's inside of the modulus, that one expects to have some sort of exponential behavior in the presence of a resonance. There is a naive approach that connects both characterizations. First of all, it's known for a very long time that exact exponential behavior is impossible for many models. And so we look for something that it's almost exponential behavior. There is a naive approach, as I was saying, that says the following: if Z equals to lambda minus I gamma is a pole of the resolvent, is resonance with resonant eigenfunction. So Z is an eigenvalue with phi and eigenvector, but it's not in the Hilbert space, so it's a generalized eigenfunction. Then if you replace in the e to the minus at phi, well, that should be e to the minus I lambda minus I gamma t phi. If you replace it there, then p sub phi of t, the probability, behaves exactly this way. Of course, this is wrong because phi is not in the Hilbert space, but this is what we expect. Now, this is impossible, as I just mentioned. So the best one hope is the existence of a state such that this quantity behaves approximately as e to the minus z eiz t. Now, these two quantities, the probability amplitude, psi in the product with e to the minus iht psi and e to the minus izt, both are equal to 1 at t equals 0, and in most cases, both goes to 0 as t goes to infinity. Remember, the set has a negative imaginary part, so this quantity goes to 0, actually. It's exponential decay e to the minus zt. Oh, I'm going to do something here. Maybe if maybe I can use, yes. So the main objective is to study this difference. For T not too close to zero, nor to infinity. You can study this difference in T point-wise or in different norms in T. And there are two norms that are interesting. The infinity norm that will give you the point-wise estimate, and the L2 norm, which has its own interest. And there are works by Lavin in 1995 and myself with our colleagues that studied this problem in one dimension where you can use ODE techniques and you can obtain estimates of this quantity when Z is a pole. And the estimates are small, the closer the pole is to the real axis, okay? And these estimates are explicit, both in the infinity norm and the L2 norm. Now, the vector psi there is chosen as a truncated resonant eigenfunction, in which region you use to truncate it has to do with the physical problem. There are many other results, especially given point-wise estimates or an infinity estimate better. I just mentioned a review by Arne Jensen in 2010. And in many of these articles, the main ingredient is a decomposition of the Hamiltonian by using the Feshbach-Lipschitz reduction and a Fermi-Golden rule. I want to mention Cataneo, Graf, and Hunziker. That's a work in where they combine these two techniques with positive commutator theory, and also they localize in energy the vector side there. So they introduce in a function g of h that localizes in energy, which we are going to also to do. But we will not use Moore theory. The use of the Feshbach-Lipschitz reduction process to study resonances, at least we could track it until work by Holland in 1975. And there are many other results which I just mentioned here. A very nice article by Bach, Froelich, and Siegel, 1998. And there are other papers that are mentioning here. But most of this work use analytic perturbation theory, and we will make no use at all of analyticity here. Here we also adapt the Feshbach-Lipschitz reduction, and we establish point-when explicit estimates when the resonances appear as a perturbation of unstable simple eigenvalue embedded in the absolutely continuous spectrum. And we make no use of analyticity. Although the techniques we chose here, as I just mentioned, can be used to several other perturbations, I will just discuss the rank 1 case. This rank 1 case appeared in the Journal of Mathematical Physics in 2017. Okay, so the second section that we called almost exponential decay is a resulting analysis, classical analysis. It provides estimates, explicit estimates on the Fourier transform on Lorentz-like functions. The function here is close to a Laurentian, okay? If kappa square F is a constant epsilon, then this quantity is, including the imaginary part, epsilon over lambda kappa minus lambda square plus epsilon square. Well, we should put a 1 over pi somewhere. With an 1 over pi, it's exactly a Laurentian. So the point is that if you replace epsilon by kappa square F with some hypothesis on F, we expect that this function, which is close to a Laurentian, will have a transform, Fourier transform, close to the Fourier transform of the Laurentian. And the Fourier transform of the Laurentian is an exponential, e to the minus I lambda minus lambda kappa minus I epsilon t. Okay. So this is our result. If you have a function close to a Laurentian, then its Fourier transform should be close to the Fourier transform of the Laurentian when kappa is small. We impose assumptions on the functions g. This is the localization function that will be used in localizing energy at the end on F and on the numbers lambda kappa. G is a real value, compactly supported function that is identically 1 in some small interval A0, B0 contained in the interval AB. That's given. The hypothesis high zero is the numbers lambda kappa converges to some lambda 0 inside of the smaller interval. The function F is complex. It's a function of 2 variables, lambda and kappa, and it has complex values, and it's bounded and continues at lambda 0, 0. And the hypothesis H1 is a hypothesis on regularity on this function. It's C1 and C1 plus alpha on a smaller interval. Helder, C1, the derivative is Helder continuous. And the hypothesis H2 is that the imaginary part of this function is 0 near, is positive, sorry, near lambda 0, 0, near lambda equals lambda 0 and kappa equals to 0. The hypothesis H2 is known as the Fermi-Golden rule, okay? And this is something everybody assumes in the results I mentioned above. Well, I think I can give you the theorem immediately. If you assume those hypotheses, then you have exponential, almost exponential decay in this sense. First of all, the equation lambda equals, I changed the notation somehow here. F kappa of lambda is what I called before F of lambda kappa, okay? So this equation for kappa small has a unique solution, lambda kappa infinity. This is the guy that is analogous to the resonance. So, okay, we have, I'm going to try to draw it here. We have lambda 0 and lambda kappa infinity, which is converging to lambda 0. and it's close to lambda kappa, close to lambda kappa. It's lambda kappa minus kappa squared times something that's bounded. Okay. So there exists a unique solution of this equation, and it's converging to, it's close to lambda kappa with the absolute value of the difference of the order of kappa squared. Lambda kappa infinity is in a smaller set interval from A0, B0, but very close to A0, B0. And when you compute the Fourier transform of the function that's close to the Lorentzian, then you get an exact exponential term plus a remainder. Psi, the term in the exponential, is given by this quantity here. Something that's real, lambda kappa in, no, sorry. Something that has a real part and an imaginary part. The real part of lambda kappa infinity, real of lambda kappa infinity, and the imaginary part, imaginary part of lambda kappa infinity. Okay, sorry, the imaginary part is the one that's giving you the exponential decay. And it's and in the real part gives you the sort of phase. Yeah. Now, the error term, I know that this term decays exponentially. This guy, but we are not really interested on the behavior of this term for t very large. For t not too large, this is the one that matters, this term here. And this is smaller than kappa squared, and even it's a little bit better in t. It's the case like 1 over t, but then you don't get kappa squared, but kappa squared log of kappa. Okay, so this is an explicit result on almost exponential on exponential behavior of the Fourier transform of an almost Lorentz function. And this is the one we want to use to establish the almost exponential decay for resonances. Okay. Well, these are precise results on the locations of the imaginary part and the real part of the psi. I think I just tell you something that's wrong. The resonance is not lambda kappa infinity, but this guy. This is the resonance. Okay, that's given here. Okay. Okay. Let's see. Oh, it's already 20 minutes. No, I can't believe it. Well, I will rush. Okay, I think I can skip that. And let's go to rank 1 perturbations. Okay, so H0 is a given self-adjoint operator, and H kappa is a rank 1 perturbation. Okay, we consider the cyclic subspace generated by psi and prove first, no, not yet, a little bit more notation, and consider this function f kappa of z, where P is an orthogonal projection that reduces H0. This is the function that will appear in the Fermi-Golden rule. We have results on the Fermi-Golden rules implies absolute continuous spectrum and other spectral theorem that will skip it. It's two spectrum. I will give you just the theorem, which is this one. Under the Fermi-Golden rule, you get exponential behavior, where the remainder is controlled here, okay? So since I have only 1 minute, is it true, Julio? Sorry.
Yes, I think so.
I'm sorry. Oh, I'm sorry. I just tell you that there are two other concepts: spectral concentration and boundaries on lower bounds on sojourn time that can be deduced immediately from the theorem. And I finish with this. You can extend the result to operators with finite multiplicity and obtain the same exponential decay, which is the third theorem here. So this is the same theorem, but for finite multiplicity theory operators. And then you can construct an explicit Sturm-Liouville operator. It's given here. Okay. If you construct a function Q on the real line with these properties, then minus the Laplacian plus Q has an eigenvalue embedded in this continuous spectrum. And then you consider dimension one, rank one operators, perturbations of it, and you can prove, you can apply the theorem. You know, in doing this stuff, you will need smoothness of the resolvent, and that comes from these boundary values of the Borel transform that I will just skip it. So I just say that the Sturm-Liouville operators is very explicit, and you can apply above theory to it. Thank you very much, and I'm sorry that I'm running out of time. Thank you.
Gracias, Claudio.
Thank you, Claudio. So, any question?
Yes, I have a question, Claudio. In your main theorem, where did you use that you are dealing with a rank one perturbation operator?
And the hypothesis of the classical analytical result. See, we have a classical sort of proto-theorem that could be about 20, but for it, you need hypothesis.
Yes.
The rank one case, you can prove this hypothesis. See? In the rank one case, the hypothesis may mention only to some function f. In the rank one case, the function f will be the reduced resolvent or something. And it will satisfy this hypothesis in the rank one case, at least.
I see. Yeah.
But it's true. I mean, you don't need the perturbation to be rank one. You can do it with other perturbations too.
As long as you satisfy the hypothesis.
Yes.
Okay. Okay, thank you.
No, you're welcome.
Other questions? No, so if there are no more questions, let's thank Claudio. Okay.
Thank you.